All right, guys, so first off, any questions on homework? Real quick, Renee, which one was that? 61?
It was 7.1. It was number,
61.
Yes, sir.
So yeah, section 7.1, number 61. I think it is. Let's see. Yes. Yes. All right. Whoa. Number 61, you can't do parts E and G to that problem because we actually skipped over exponential distribution. So I'd seen somebody earlier, they put in analysis, remind me in class, and they forgot to remind me. I forgot it. So if you have any trouble number 61, that might be why. Because it's an exponential distribution. We didn't really, we kind of decided to throw that section out. It was extra. I was hopeful I could get to do it, but it was too much. So number 61. Hey guys, how you doing? Right. Yeah, attention up this way. Number 61, 7.1. You don't have to do part E and G. If you do it and you do it successfully, yay! It means you looked up the formulas for exponential distribution. I love it. You're awesome. But if you don't want to, you don't have to. It's not a part of the course anymore. Let's do. What's that?
I said I'm glad for this quiz.
I think that's what you said, yes.
Yeah.
I don't care how you feel about it. You want more grades. Yeah, the more grades, the better. I had a class where the only grade was the oral final exam. And that was horrible. That sounds terrible, but it's where they give you a problem. They don't do anything weird. They give you a problem, and then they put you in a room. Did I ever tell you this story? I've told this story so many times. Because the lady next to me was a good friend of mine. She had a nervous breakdown halfway through. So I'm in there trying to do my work, and she's over there in the next room going, oh my God. That's awesome. Anyway, so be thankful you don't have that. Be thankful for the quizzes. Wish that there were more. Yes, ma'am.
I had a question on 8.1, number 102.
Oh my gosh. All right, here it is. All right, so let's see. Conducts a yearly census, smaller percentage. So it says they estimate with. Oh, let me put this up here just in case you guys don't have it. Using this bad boy anyway. Yeah, cool. So number 1 and 2 is right there. 90% confidence of a mean household income falls between those two values. Find the point estimate. So what's another name for the point estimate? Anybody who's actually read the book? Second? Oh, the mean. Good. So point estimator is like another name for point estimator is our best guess. And the best guess for the average is the average that we found. In a confidence interval, when you make a confidence interval, where is the mean in that confidence? Where's your sample mean?
In the middle.
In the middle. Why is it in the middle? Because you start from the mean and you add and subtract the same amount. So of course the thing is going to be in the middle. So this is really to translate. Find the sample mean that we found. So So they give me that the confidence interval goes from there to there. So the sample mean must be in the middle of those two numbers, right? And that's a very basic math. So it was really just a translation. Translate from what they say to what it means. And then it becomes a simple, can you find the middle of those two numbers? And then what's the error is the amount that I add and subtract from the mean, right? So if I had a confidence interval that was from 5 to 7, what must the sample mean have been? 6. Just to give you a similar problem with easier numbers. The sample mean must have been 6, and what must the error have been?
1.
1, because it's up 1, down 1. Now do the same thing we just did there with those numbers there. All right? I like it. So it's a good question, because I don't think I said the words point estimate yet. But that's just like another way to say point estimate is best guess for the mean. And that's going to be our sample mean. That's our best guess. Okay. Anything else from homework? Yes?
Back to number 61 on 7.1. I don't understand how you're supposed to get like B and B because they don't give you the standard deviation.
Oh, so I was considering just throwing this problem out, but it's definitely not now. That's just too bad. But if you just look up the exponential distribution, it actually tells you the standard deviation. It's awesome. They just tell you the mean here, don't they? Right? So if you go back and you look at exponential distribution, it's back in chapter 5.
Isn't the mean divided by square root of the sample size?
Well, that'd be the standard deviation.
The standard deviation is the same as the mean. You gotta love it. Bam.
Oh, nice.
Yeah, so it's awesome. So the mean is 0.88. So it's the standard deviation, 0.88. So we didn't talk about how to get probabilities from an exponential distribution. But why am I saying that you can do part F?
Because it's an average.
Yeah, even though it's not quite 30, exponential distribution is really nice. It's a really nice distribution. So you don't need quite 30 to make it normal. So in part F, it becomes a normal distribution. So part F you can do all day long. You know the mean is 0.88. You know the standard deviation is 0.88 divided by the square root of 25. Right? We have to change standard deviation sigma over square root of n. We have to change the standard deviation. Alright, so if the only problem you're having trouble with is 61, you're fine, because that's actually referencing a distribution that we didn't fully cover. But now you know that the mean is the same as the standard deviation for it. You can do the rest of that problem. I have faith in your ability. You can do it. Push yourself. Anything else from homework? Is it going okay? You doing the homework? It's the best way I understand this stuff is actually do the homework. I'm sure you're getting tired of me saying that. Yes?
On page 455, 109, it gives like x bar and s, and there's two numbers after. I don't know what the second number is, like under the table.
Oh, here?
Yeah.
That's the standard deviation, it looks like. So let's see. Yeah. I mean, that's the sample mean. There's the sample standard deviation.
Why are there two for each of them?
2 for each. How do you mean?
Two numbers.
Yeah.
251,854, 23 cents. Yeah, look at the size of your data. So it makes sense that the mean is going to be in the 100,000s.
Oh, I see how she got confused because they like spaced
Oh,
it
yeah.
a little too far.
Yeah.
It looks like it's...
Again, typesetting, you get what you pay for, which was here. Yes?
That one though, it says that the table shows the selection of 20 leadership, and then there's 30 members.
Oh, okay. Well,
Is that like,
typo there for the 2 instead of 3. Sure.
I
Yeah,
I
1,
wasn't
2,
sure if
3,
that
4,
was
5.
the
1,
reason.
2, 3, 4, 5. Neato. Total receipts due in the second floor range selection of 20, so it should be 30. Looks like, yeah. Okay. That's important because n should be 30 because there are 30 data points here. I like it. Cool. But if you did it already and you used 20 for n, you're fine. I understand. Because it did say 20. Okay. Anything else from homework? Yes?
For what's going to be due on the next exam, does that start on 8.1 or is there going to be 7.2 where you told us to stop?
Yeah, so the chapter 7, where am I at? Oh, so I already told you how this changed. So 7.2 is extra credit, so 7.3 is going to definitely be due. You with me? 7.3 is definitely due still. 7.2 is extra credit, so you can do it or not.
Wasn't section 4.4 extra credit too?
Maybe. It's a while back. I can't remember right off the top of my head.
I think it's
Okay, cool. Let me think. What else do I want to say about this? We're not going to have any problems from 7.3, because 7.3, if I remember correctly, was just
Extra credit.
No, 7.2 is extra credit. 7.3 was just further using the central limit theorem. I don't know if you guys remember that. So 7.1 was the central limit theorem, and they gave central limit theorem problems. 7.2 I made extra credit. 7.3 was just more problems with the central limit theorem. So I didn't make the homework due, so you had time to finish the other homeworks. But 7.3 will be due, but there just won't be any questions on. I already tested over that stuff on last. Yeah, whoever's asking that. All right, anything else from homework? Okay. All right. Last time we made it up through section, well, let's see, we actually almost finished chapter 8. So I want to finish chapter 8 up. And then get into chapter 9. So what do we have so far? Can you guys tell me how many confidence interval equations have we learned?
2, I believe.
No? I guess the question could be interpreted, you're like, I only understand one of them, so I only learned one. But we talked about 3 really. There's 2 for the mean, and there's 1 for the percentage. And why are there 2 for the mean? What's the only difference between the 2?
Sample population?
Good. Z-score and T-score. So the very first formula was the very first thing we did, and it was really based on an old formula that we've used before. That's why I like to start there. And it was just this guy here. That looks a lot like mu plus Z sigma. So we actually built this from this. I don't know if you guys remember. So that's the basic idea there. Then we said, I can't remember what the order it is, but if I don't know sigma, if I only know S, that's when we have to use T-scores. And how are T-scores always related to their Z-score cousins? True, that's where they are on the chart, but how are the T-scores related to what the Z-score would be?
The bigger you get,
They're a little bit...
smaller.
Siri says, I do not understand. So how are T-scores related to Z-scores? Why were they invented?
There's a
When we
brewery
don't
involved.
understand.
When we don't know the population standard deviation, so they have to force my confidence interval to be...
Cover your eyes.
Bigger.
Yes, so it must be bigger. He's got a big ol' ass, right? So my confidence interval, so my T-score will always be a little bigger than the Z-score would have been. And you can see that when you look at the chart. You look at the bottom of Z-scores, when you go up from there, they get bigger and bigger and bigger. And then when you got a really small sample, it's going to be huge. It's like, you don't know shit, man, and make your confidence interval crazy big. Somewhere between 2 and 848. Oh, that's useful. Thanks. Maybe get a bigger sample. Bring that sucker down a little bit. All right, maybe. Okay. All right. There's no reaction. All right. And then finally, this guy. We developed this formula. So this is a little bit different, but it looks sort of like this idea, with NPQ, remember the standard deviation for a binomial square root of NPQ? But then it kind of is, this is not why this is true, but you can sort of remember it this way. That's got an n on the bottom, so this is going to have the n on the bottom. So it's normally NPQ, but this is PQ over n instead. So that's the three main confidence interval formulas. So you're going to have those sitting on your formula sheets for the next test. And then next to this, we did, what if I want to know how big of a sample I need? So we solved for n. So we did a problem like that. How large of a sample would you need to be within 0.1 of the actual mean, right? So the error would be 0.1. The magic word there was within. Very often they'll use the word within for the error. So we did a problem like that. So hopefully some of you guys realize I should be able to get a formula just like that from this guy. And to be honest, you could use it for this guy too. It would just, instead of z, there would be a t. Instead of sigma, there would be an s. Ooh, so it would work the same way. So it's really the same formula. So how would I get the formula for this guy? Well, what's the error for this third guy? What's the error? What piece is that? What piece of that is the error? This entire thing here, right? That's the error. It's this, give or take that. So this is how much I think I'm off by. Okay, I like it. So that's the error. How do I solve this for n? Oh, that looks yummy. I like some of your faces. Yeah, like, I left that behind.
Square root, or,
First good thing to do is to kill the square root. I like it. How do you kill the square root?
By square.
No way. Alright, so square both sides. So I get e squared equals z squared. Can you close the door for me? Nice one. I'll be part of all these conversations going by. And what are you here?
everything minus the root.
Yeah, because that squares the z and the square root kill each other. Alright, this is not intense algebra, but this is algebra. It's useful. It's crazy. It's not just for math teachers.
E squared and
Is the same guys just walking the other way now?
Yep.
Alright, sorry.
it was like crossed.
And I'm like that. And then I'm done. So there's my n equals z squared p hat q hat over e squared. That's the formula for how large of a sample do you need to be within 2% of the real percentage, blah, blah, blah. That would be the question they would ask for that. So this is, again, just to remind you guys, this is kind of like a feasibility study. If I want to be within 0.03 of the true length of this fish, how many fish do I have to get? If this is 800, maybe that's okay. If this is 8 million, I don't think so. Let's be a little more tolerant on how far off we are. It's a feasibility study. Is it feasible to get that close to the real thing? See, how large of a sample would I need to take? Right? Do I have the resources for that big of a sample? Maybe. All right, so let's do this. Let's try an example of this, and then we'll get into chapter 8 or chapter 9. Please do chapter 8.
Can I ask you how you got the egg and the e squared switched?
Oh yeah, so I would multiply both sides by n, right?
Okay, yeah.
And then I would divide both sides by e squared. So that's a beautiful thing about algebra. If I have something equals something over, so I can just switch these two. It's a shortcut of what would happen anyway. It's kind of like cross multiplication, except you cross in the night. You can make whatever sound effect you want when you do it.
Awkward test taking.
Huh? Yeah, I know. I love that. That would be awesome. Ooh, what? All right. So let's do a problem with this here. Last time we focused on the t-scores. So if you weren't here last time, I highly recommend that video. So here's the thing about, somebody remember, how do I tell? So two things. For an n p hat q hat problem, what do I have to check for it to be normal.
If it's above
Greater than
30,
If what is what?
if the sample size?
That's for the means. I can check to see if the sample size is bigger than 30. That's central limit theorem. What do I have to check for NPQ?
It's greater than 5.
What's greater than 5?
NP.
Yeah, NP, NQ, greater than 5. And if they're hats, you just put hats on them. All right, they're socks, you put socks on. Whatever the P and Q are wearing, that has to be true. And I talked last time, hopefully it makes sense about, that just pulls it out to the center, so it's got room to go up and room to come down. So it kind of makes sense. Why is it exactly 5? I can't get into the details for that, but the idea of it pulling the mean out from the walls, so there's room for, that's what that does. So if this is true, I'm allowed to use Z-scores. If it's not true, I can't do shit. So I just never use T-scores. Sounds like a note. Never use T-scores with an NPQ problem. Which is beautiful. Let that be nice. You always use Z-scores as long as it's known with an NPQ problem. Yes, ma'am?
Does the NP have to always be greater than 5 if you never be equal to it? For it to be normal?
Yeah, I said last time, because some books say this. So you can imagine, if it's 5.00001 and that's okay, why is 5 not okay? So it really kind of depends on which book you use. 5, it's just like 30. Some books say greater than 30. Some books say greater than equal to 30. So it's just, to a degree, it's sort of arbitrary to a certain degree. They just like 30 because it was a round number, to be completely honest. It actually was like 29 point something, I can't remember. 30 point whatever, right? Anyway, so the short answer is, technically, it does have to be bigger than 5 for this book. I like it. All right, cool. For it to be exactly 5, that's not going to happen very often. That's very unlikely to happen. All right, so let's try this out. Let's try a problem. It's really weird how little I have to tell you to do a problem like this. So let's say, example, we poll 517 people and find 208 plan to vote for Bernie Sanders. Feel the burn? You guys know who Bernie Sanders is? Right? Mad Scientist looking dude? It's one of the candidates, one of the many out there. Find the 98% confidence interval, or the true percentage who will vote for Bernie Sanders. So on the TV it would say 40%, 44%, and then the bottom say plus or minus 4. So now we understand, now we know, we can actually calculate that plus or minus. We can calculate the error. It's not just, they didn't just go, I'm not sure, put a 5. No, they actually had to calculate it based on what they did. This is all I got to tell you. This doesn't feel like much. That's all I got to tell you. Can somebody help me out? So what do we need? If it says confidence interval, I want one of the 3 formulas that has the plus or minus in it. That makes sense. And of course I want the one, in this case, that's got the percentage in it, right? The P and the Q. So I can kind of narrow it down as to which formula I want to use. And then the formula tells me what I need to figure out. So let's see, what do we know? What's N?
507.
Beautiful. It's not 208, right? So what can I figure out from 208?
We can divide that by
I can figure out, exactly, figure out what now? P
divided by
hat.
oh.
208 divided by 517. So what's the percentage for my sample that will vote for Bernie? 208 people out of 517. I like it. Cool. So somebody else, what's that? Somebody help me out. 40? Exactly?
Point 402.
There you go. So 0.402. I don't know if you remember. How far out do I want you to take this? At least 3 places. Just another weirdness of your teacher. That's too bad. You picked a weird one. And then Q hat would have to be what?
309 over 5.
Even quicker, it would be
Oh.
5, 9, 8. The rest, right? P and Q have to always have it to be 1, no matter what the hell they decided to put on themselves. Okay, I'll use one more because my jokes are for me. So if one more person laughs, it's even better. So now I've got everything I need except for what? What's the one thing I'm missing?
You're missing the z-score.
Z-score. And where's the Z-score going to come from?
A chart.
Well, where from what they told me in the problem?
From the 98%
I like
confidence interval.
So for a 98% confidence interval, what do I have to check though? I haven't checked it yet. What do I have to check to make sure that I can use the chart? And how do I check to see if it's normal?
NP is,
Can anybody tell me exactly what it is without doing any work? The answer is sitting up on the board. It's in the first sentence.
517.
That's n. So I need n times p hat. How did we get p hat? Didn't we do 208 divided by 517? So if I multiply 517 by p hat, I get 208. It's awesome. So it's just staring you in the face. But if you do the work, it'll come out to be 207.93 or something crazy, which it's trying to tell you, dude, it's just 208, right? So NP is 208, which importantly enough is bigger than 5. Check. And Q hat must be everybody else. How many is everybody else? I like it. Definitely more than 5, but specifically it's how many more people?
309.
309. That's greater than 5. Check. And that check tells me that I have a normal enough distribution. I like it. So this together, this tells me it is normal enough. Right. Sounds like parents with a kid. He's normal enough. Does some weird shit. He's normal enough. All right, let me stop there for a second. So it's desperately important that if you were here last time, I discussed why this greater than 5 thing, why does it make sense? And if I ever want to use the chart or anything associated with the z-score chart to do something, I have to know it's normal. So a big chunk of statistics is dealt with how to tell what kind of distribution you have. If it's normal, you got this whole set of stuff you could do. If it's something else, you have this whole other set of stuff you could do. If it's nothing, you got, well, a little bit of something you can try to do, right? So that's my check for NPQ problems to see if it's normal enough for me to do anything. So now I can use z-scores. For a 98% confidence level, what's the z-score? Sure. Who's got a slightly different number, doing it a quicker way?
5, 0.
No, 233 I agree with. You can use the t-score chart, remember? No.
3.326.
Yeah.
Do you have extra t-scores?
Yes. Anybody else need a t-score chart? All right. So let me remind you guys. So again, t-scores exist to cover our ass for when we don't know the real standard deviation of the population, right? So they're always going to be bigger than the z-scores would be, but the bigger my sample is, which is, this is n minus 1, but this means that as my sample gets bigger, I need them to cover me less and less, because I'm more and more sure about what I'm getting from my sample. If I get a bigger sample, I'm more sure about what I'm getting from it. So as it gets bigger, the t-scores get smaller, and in fact, when I get a really large sample, then it's basically the right standard deviation that I have. I don't need a t-score anymore. They become z-scores. So if you look at this, if I want a confidence level of 98%, what's alpha? 2%. So I want 0.02 and 2 tails, or 0.01 and 1 tail. Either way you look at it, you're here. And if you go all the way down Your z-score is 2.326.
Z? I thought, wait, is that
What?
I'm getting confused.
So if I stop, I get a, if I stop somewhere, that is a t-score. If I stop.
Yeah.
As my sample gets larger and larger, I am more sure about what I measure from my sample. So as my sample gets really, really big, the t-score becomes a z-score. So these are z-scores at the very bottom.
So why would you stop at 500?
When it starts.
Say again?
when it
I
starts-
said, so why would you stop at 500 if you have 570?
I didn't stop at 500.
No, why wouldn't you? Because isn't that the sound? What
So
is-
again, okay. Can you use z-scores with an NPQ problem? I mean t-scores. Can you use t-scores? No, you can't. You don't, right? You don't. If it's normal, then I can use z-scores. So I want to get a z-score. So totally, you guys can get a z-score from the z-score chart. That just makes sense. But I desperately want you to realize the idea of a t-score explains why it makes sense that z-scores are on there. When my sample gets really big, I don't have to use a t-score anymore because I'm really certain about my standard deviation. So I can just go ahead and use a z-score. The last row on the t-score chart are z-scores. Yes, ma'am.
And can you go over which tail you use to find that?
So alpha is the amount in the tail or tails. So how many tails does a confidence interval always make?
2.
2. So if I want 98% confidence, what's alpha? 98% inside,
2.
2% outside. So 0.02 in 2 tails. So I want 0.02 in 2 tails. Now if you think 0.01, because you cut it in half, then that's in 1 tail, and either way you look at it, you're in the same column. I like it. So one reason why I'm trying to get you guys to kind of filter over to the t-score chart is just so you get more used to the t-score chart, because the top of it is a little confusing if you're not careful. You got to pay attention to, do I have 2 tails? If it's a confidence interval, yes. But if you cut it in half, then that's the amount in 1 tail. Maybe. So let's talk real quick. If I had a 95% confidence interval, what's alpha?
5%.
Yeah, alpha would be 0.05
Like that's all I remember.
in 2 tails. So which column would I use? The middle column. Now, what if somebody cuts it in half and says there's 0.025 there?
Then you
That's still the same. It's still the middle column, 0.025 in 1 tail. So I want you to get used to how to tell the difference between the very first row and the second row. It just depends on how many tails you're going in looking at. Yes?
What do you do when the number of your alpha isn't on there?
Oh, have you run into that?
I don't know what that is.
All right, you won't. Yeah. T-scores, you can imagine, I don't know if you can imagine this, but for every degree of freedom, you would need an entire z-score chart's worth of information. So look at all those degrees of freedom. So if I did the t-score chart as detailed as the z-score chart, it would be a lot to carry around. So we kind of did a trade-off. We said we'll put the most commonly used values up there, and then if they're not that, we'll have to use technology to help us, because the calculator just eat it up and spit out a t-score. Cool. I like it. Some of you guys are like, well, why don't we just do that? Well, because then you don't learn as much. Yeah, that's my whole point. All right. Cool. Maybe. Okay. So either way you look at it, you get a z-score. You can either use 2.33 or 2.326, like we got off of there. Right there. So now I can put this bad boy together. I've got everything I need to throw into this. So how do I set up this formula? P hat was
0.4.
Yeah, 0.402. Give or take. Z-score, we just looked that up.
2.326.
And then P hat, of course, is still 0.402. Q hat, 0.598. And N was 517. Now here's where I got to be careful, because the parentheses will screw you over a bit. If you have a newer graphing calculator, then it actually makes the square root sign get bigger, which is nice. If you have an older one like mine, it just is a parenthesis. You don't want to close it till you're done. So let me put this up here real quick. Oh, while this thing is booting up, let me give this out here. This is the second part of the homework. Might as well give you guys this thing. Oh. Alright, let's see if this guy is woken up yet. So let's... Alright. So just like before, I recommend you do the error first. You don't have to if you don't want to. So let's see, we got 2.326. So my calculator, like I said, has got the older operating system on it. If you want to call it that first, yeah. So it has a parenthesis. I just cannot close that until I got everything underneath the square root in there. Okay. 517. So then I close it there. So I got all that's supposed to be under the square root. I've got it all in between those parentheses. Right? If I close it too early, the calculator stops the square root sign, and anything after that is outside of the square root sign, and that's a bad way to be. Right? If you do that, you'll have a bad time. So I got that for the error. So what you guys got?
Yeah.
Yay! So that's what, make it a more human way to say the error is roughly
0.05.
5%. So it's give or take 5%, right? Roughly. So we have, so my 0.402, give or take 0.0502. Right? And then, so then what's your interval? 3519? 18 something, yeah. Up to 0.45022, yeah, thank you. Let me stop there for a second. Alright. So then, from this, I know I haven't written the conclusion yet, but from this, does it look like a majority of people will vote for Bernie Sanders?
No.
Majority meaning over
50%.
I love it. You can't make too much out of the specific numbers that are the low and the high. But this does give you an idea of the range. It's sort of like that. Remember I talked about the hurricane and the cone of uncertainty? So that gives me an idea of the range where I expect it. It could totally go outside of there. And thankfully, like Patricia, I don't know if you heard, but down in Mexico, it didn't kill anybody. It went over a very unpopulated area, right? The largest hurricane ever recorded, I think it was. Holy shit. Hello, global warming, climate change. It doesn't exist. What the hell? Sorry. I don't want to step on anybody's toes if you can't accept the reality. So, how do I write the conclusion?
Our interval.
Good. At the interval.
Contains
Interval who to what? 35.2% roughly to
45.2%.
contains the true or the population, however you want to say it, percentage
Mean.
of people who will vote for Bernie Sanders. Now, I don't want to see the word mean in here anywhere because it's all about a percentage. It's either about a mean or it's about a proportion, a percentage, right? So this contains a population percentage or true percentage of people who will vote for Bernie. Feel the burn. All right.
What's the difference between P and Q and then P hat and Q?
I love it. What's the difference between this and this?
Oh,
So P is like this, that's population percentage. P hat is like that, that is a percentage from a sample. And that's why I had to put a hat on what I found from this, because this was a sample. Kick-ass. I love it. So that relationship is really nice to keep in mind. That's how they are related.
Sorry, Jim.
Cool. All right. So 5% is pretty big of an error for this kind of thing. Normally it's 3 or 4%. So now I want to say, how many people would we have to talk to be within 3% of the true percentage instead of 5%? If I talk to 517 people, that got me within 5%. But now I want to be within 3%. Let's see. So my formula is this guy. Notice if I ask you this question first, do you know what P hat and Q hat are? We had to do this before we knew what they were, right? Make sure you understand what I'm saying. So this formula requires us to use P hat and Q hat, right? So if I ask you this without making you make a confidence interval, how do you know what P hat and Q hat are? So if you don't know what they are, what do you think your best guess is for them? If you don't know the percentage of men in the room, in the next room over with people in it, what's your best guess? 50. So in general, your best guess is 50-50. So if you don't know what P hat and Q hat are, you make them both 50%. Mathematically, that makes N the biggest, which makes sense, because the less I know, the more conservative my math should come out to be. But we did what's called a preliminary study. We talked to 517 people. We got an estimate for P hat and Q hat, so now I can use those in the equation. It's going to make N a little smaller than if I didn't know. So the more I know, the less people I should need, the less sample size I should need, or something. They kind of go together. So now you just got to plug and chug everything. We know what z-score is. We know what P hat and Q hat are. What's the E? Yeah, I want to be within 3%. So don't put a 3 in there. Right? Math doesn't really know percentages. That's a human convention. The actual number is 0.03. So let's see, N would be, what was z-score? 2.326 times P hat, Q hat, all over 0.03 squared in this case, because I want to be within 3%. So that's what I want my error to be. I want to be off by that much. And plug and chug. Now, how should it be related to 517? Should definitely be bigger. If you want to have your confidence interval be even more accurate, even more precise, your sample's going to have to get larger. I predict it's going to be a decent amount larger.
1,434.
Yeah, almost 3 times as large, right? It sounds like. Is that what you guys, anybody else trying that out? I want at least 2 sources to make me feel better. So let's see if we get 2.326. The most common mistake I see is people square the P hat and Q hat, but they're not squared.
What did he say?
1,434.
Yeah. Well, I got 30. I got 45.
Yeah, that's what I heard.
I got 1,445.
402, did I put 4? Oh, put 408.
1,445.
Yeah, I got 1 4.
402, right?
Yeah.
So 1445. So what is it?
1,446.
Kick ass.
Because those round up whenever.
So how many more would I need? Well, that minus that, that's how many more people I would need, right? I've already talked to 517, so I only need to talk to 900 and something. Yeah.
What did you press on the calculator to get your what you plugged in before?
Second enter.
Oh, I'm sorry. Yeah, second enter. If you keep hitting it, it'll go up through. I think it goes through the last 8 entries. If I hit second enter, it'll go bam, bam, bam. Because that's awesome. Because especially in this class, the formulas are only going to get larger with more parts to them. So it desperately sucks if you put a plus there and it was supposed to be a minus. All you got to do is second enter, go over to it, put a plus there. Beautiful. Kick ass. Good to know. Okay. All right. So I would never teach this like to people that don't know it all and just say, "Oh, just plug and show you." But at the end of the day, if you understand the ideas behind it, that's a bonus. But confidence intervals, they have to basically tell you everything, except for 1 or 2 things. Here, they told me everything except for the z-score, which I always get from how confident I want my, what level of confidence I want. And they didn't tell me p-hat, but it's easy enough to get the percentage. Just divide what I saw in my sample, right? So they have to tell you everything. It's kind of nice. And then you just got to put it in the right formula in the right place. So that's what statistics, and I told you this on the first day. A lot of Greek letters that you have to understand what's supposed to go in them, and you have to know when to use which formula, right? That's what gets people down in stats. The actual work is not that crazy. I can just hear some of you like, were you in the same class as me? It really isn't. Okay, so I want to sneak into chapter 9. Horrible at sneaking because I just told you. Okay. So let me kind of build up to this. I have a handout that explains the 5 steps that are needed for these problems. When I took stats, they were at 8 steps. So you're welcome. I try to truncate it a bit, right? The book, the big thing I don't like about the book is that it relies way too much on the calculator. And I know some students would rather just push buttons and get numbers, but hopefully some of you guys understand why I don't let that happen. And even if you don't, oh well, I won't let that happen. So the main idea with chapter 9 is an ability to test a claim. So now I want to be able to, and confidence intervals sort of give me an idea of how to test a claim. We last time we were together, we had one confidence interval and the other one, and it was evidence that they weren't equal to each other because they didn't overlap. But I need something that's sort of just that's just like a throwaway at the end. You're like, oh yeah, I can kind of see. But this is built for evidence to show that a claim is right or wrong or what it looks like. So testing a claim is the main idea behind chapter 9 and 10, by the way. Let's focus on 9 for right now. So what do I mean by this? So let's say that, so here's a nice classic problem. Let's say that I do an SAT class. Right? I do like an SAT workshop. And I claim that my students, what is the SAT? I don't even know what the scoring changed since the last time I took it.
24.
That's not, max is 2,400? Okay. Well, they just threw some more points in there. Essays and stuff, it's too bad for you guys. SAT workshop, my claim is that my students score higher than, let's see, so let's say 1,700. I don't know what the average would be nowadays.
About 1,500. About 1,500.
15? Okay, good. So this is even more than average. I like it. All right, you guys understand so far? I mean, this you hear this kind of thing all the time. The real classic one would be like a drug test, where we make a claim that my new headache relief medicine will bring relief in 5 less minutes. You know, you take it, and even before you took it, you're feeling better. Oh, I feel better already. Right? So that's my claim, and then I want to test the claim by giving a bunch of people the medicine and giving the other people a sugar pill and seeing what happens, right? And the sugar pill people, they get way better. I'm like, what the hell? Take sugar pills. You're great. So how would I test this? What would you do if you wanted to test this claim?
Ask students what their score is.
All right, good. So you would, and where would those students come from?
From the workshop.
Yeah, from a sample of the students who actually went to the workshop. I like it. You guys kind of with me? So you would take a sample. So to test the claim, you would take a sample from the workshop students. And find their average, right? Now here's the key part. What I'm about to do is a key part to understanding the idea behind this. Let's say I take a sample of 112. So it's definitely a nice, good, robust sample size, right? As I randomly selected them. I didn't just select people that I knew were smart. I just randomly selected them, right? And it's not me. I own the workshop. So to make this nice, I'll bring in an independent third party. All right? Okay, you guys still with me? All right. And let's say I find X bar is 1711. Do you understand why I can't stop there? Why can I not just stop there? So some of you guys, which understandably, if anybody's like, that is bigger than 1700, done, next case. Right? Grinder out. You guys, does anybody, now, if you feel that way, don't feel bad. It's not quite right. Because is that the actual average for all the students who go to the workshop? Even though I randomly selected my students that I picked for my sample, what could have happened? I could have just happened to pick
the highest one.
A bunch of higher graded ones, right? Or even if not, the average fluctuates for any sample, right? It's going to dance around the actual average. So is it possible the actual average is still below 1700?
Yes.
All day long. You guys still kind of with me? So this section, this chapter is my favorite because it's the most immediately true to life, plus it brings in every damn thing we've talked about so far. So automatically it's going to be a lot of your least favorite, but oh well. I understand, right? You're like, shit, man, just focus. No, it's going to be all right. So what I need to do to show that this is strong enough evidence, and this is why I made such a big deal about what z-scores tell you, is to show that that is far enough away from this to say that the actual population is bigger than this. So not only does my sample have to be, whatever the claim is, but in this case, my sample would have to be bigger than 1700. That's not